for the invitation. It's a great pleasure to be here. Fantastic place. Having a great time so far. To the point that I have followers, so people with t-shirts of things. That's great. Great support.
Your loyalty is definitely. I'll see you in my office.
Okay, so I'll keep talking for long. Alright, so I'm gonna talk in probably one of the best places on earth to talk about these topics. So I'm really happy to be here and to share with you my view on this. So I'm gonna talk about null hypersurfaces and how to quantize the gravitational phase space of a null hypersurface. This is a work in progress. It's an open work environment with plenty of ideas and a lot of directions that open and close and open, so there's a lot of fun there. I've been thinking about this since 4 years more or less. We had 2 papers, one last year and one this year. Last year was about classical things, so really just GR. And this year was more about, let's talk about quantization in some perspective and how to understand it. It's been, both of them are in collaboration with these 2 great friends. We've been working on a lot of stuff together. That's been a great pleasure. So, what I'm going to try to set up here is an approach where, if you want, I try to go back to a very old problem, which is quantizing gravity, right? I'm going to do it very simply, starting from a null hypersurface in the bulk. And although the problem itself is as old as you can imagine, kind of the tools and the way we're approaching it is kind of more modern. And in particular, the focus of null physics is relatively new. Not in the sense that we're the first one, but there's been in recent years, really in the last 20 years, a lot of developments and discoveries in understanding null physics and the property of null physics. So I'm going to also try to use my holographer hat, because really that's my camp historically. So I'm going to try to think of a null hypersurface on its own, intrinsically, or what we can induce from the bulk, and kind of forgetting that there was a bulk to begin with, and just thinking intrinsically in terms of the hypersurface on its own. And in this sense, definitely preaching to the choir here, but I like to see whether we can push in the bulk concepts and tools that we've been using in the conformal model, okay, to create really a local holographic statement. But I'm going to also use some influence of canonical quantization and things that have been arising from a different community many long times ago in trying to quantize the gravity on a space like hypersurface, the usual structure that we all studied, the Hamiltonian constraint as Lagrange multiplying, the idea of formalism. All these kind of tools will also be influencing our analysis here. And why are we doing this in 2024? I think that's the very first question. It seems like an old problem, as I was saying. And it's really because, and I insist, the math of null hypersurface really took us a while to figure out. When I say us, I mean the community. So, whereas the math tools were at our disposal, kind of understanding the physical law of gravity of the null hypersurface really took us a while. The phase space was a very long endeavor that I'm going to discuss. And so really the time is now, it's mature enough to try to approach this. And the main message, and some people in the room have already noticed that years ago, is that the physics underneath null hypersurfaces is very simple. The math is hard at the beginning, but the physics is really simple. And the 2 characterization that makes it so simple is the notion of ultralocality and the notion of conformality. And this is really what I'm going to exploit all the way in the classical phase space to preparing the ground for the quantum application later. What is ultralocality? Ultralocality is the statement that the future of an observer sitting on a null hypersurface is just the null ray in front of himself, or herself, and that happens for the other one. And so, strictly speaking, it's a one-dimensional system. Although the system was d plus 2 dimensional in the bulk, d plus 1 dimensional on the hypersurface, is effectively a one-dimensional system in time. This is really to be contrasted to space-like, where the 2 points separated, they will interact in the future like this. On a null hypersurface, if I have my cut, you can really think of pencils. In the literature, we've seen the notion of pencils, the notion of null hypersurface, of points or small region on the cut, and its filter is just these tubular things emanating from it. And this is going to be very useful, and we're going to see that also gravity undergoes ultralocality. It's a feature of null physics. Electromagnetism, scalar field, anything goes under this. And the second is conformality, which is the usual thing. There's no notion of intrinsic length along the null time, and so there is inherently there is some sort of conformal symmetry lurking around that we can exploit also for gravity. Okay, these two features combined together, combined with the understood mathematical structure, lead really to some very simple physical system for which we can at least attempt to say something at the quantum. That's kind of the spirit. Okay? I'm sorry, I should have said interrupt me, ask question. On purpose on the chalkboard to enhance discussion. I had slides, but I prefer chalkboard really to interact more. I'm happy to stop any time to make people understand. Okay, so let me start. I'm going to talk about a null hypersurface. A generic null hypersurface in the middle of the bulk will develop caustics at, in principle, finite times. So what I'm thinking of doing is to tip off, and so I'm discussing a portion of a null hypersurface between two caustics. I'm going to tell you in a moment why I need to do that. I'm going to call the null hypersurface N, and I'm going to take 3D, such that the bulk is 4 dimensional. Why do I need to do that? Because the mathematical tools that I reduce is the notion of a so-called these days Carolla structure. It's just a rebranding of math of null hypersurfaces that we did to get more citations. And yeah, this was already in Ashtekar papers in the 80s, but we just understood it in this language of Carolla structures. And the Carolla structure is defined by a null vector field that is non-vanishing. That's the reason why I need to exclude these tips, because at caustics things can go south, and that is in the kernel of the metric, such that this metric is a degenerate metric. This is the one that you use from the bulk, and its non-degenerate part is this Euclidean metric that lives on a cut of the null hypersurface. Okay, so these two data are the geometry of the null hypersurface. You should morally think of them as the induced metric on the hypersurface that is time hyperspace. They define your geometry. Now, I cannot lower the index, so I need to introduce by hand a one form, and then just do it at the quantum bundle level to work well. I will call that K. This one form K allows me to talk about cuts. So the volume form of the entirety of the hypersurface can be written as the one form K wedged together with the volume form of the cut. Okay, this is the cut organized accordingly to K. Okay, and so this one form K is called also an Ehrenschmann connection. The tripole LQK is called a ruled Carolla structure. But this is just the geometric data that you need to describe an hypersurface. Okay, so now I cannot raise a lower indices as I was saying to you. So let me just see in a previous example how we do it. Then introduce a very important quantity, which is called the expansion tensor. It's just the Lie derivative along the level of QAP. And now the object with the mixed indices, which I need because I want to take traces, is defined uniquely by the two conditions, theta B equal to 0 and theta B QBC equal to LBC. Okay, you solve those, and it gives uniquely the object that one index down, one index up. And now once you have it, you can decompose it in its trace part and its traceless part. The trace part organized accordingly to the projector, which a posteriori I should have called chi, but I called it Q already so many times that I don't want to change notation. It's literally the projector to the space orthogonal to K and L. So QAB, KB 0, LA, QAB 0. Okay, so if the projector to the base, where the cut lives, I call it this cut. And now this is the expansion, and this is the shear, traceless shear. These are really the expansion and shears that enters in the equations of motion I'm going to describe. Okay, so this is the geometric data. The last important ingredient that I have to tell you, and as you can see already, I'm very much holographic, where quotation mark in spirit, because I never introduce a pattern. I'm describing intrinsically the null hypersurface. I'm going to see that the bulk provides for me information about, say, the radiation profile, or what in affinity you should choose, etc. But I'm going to always try to rewrite all these conditions as an intrinsic condition of the null hypersurface. That's kind of the logic I'm using. And especially, for instance, when it comes to the connection, on a null manifold, on a three-dimensional null manifold, there's no Levi-Civita theorem, so we have to backtrack a moment. There's no unique torsionless and metric-compatible connection, so we have to think about which connection to choose. And this is where I use the bulk notion. I simply define carefully what, of course, not to need this object. I define a projector from the bulk to the null hypersurface in a specific way, and I call this D. What are the properties of this object? Given my choice of the projector is torsionless, and I like that, and it's not metric compatible in a very precise way. It acts on the volume form. I created this one form omega A, which contains two very important quantities. Along K, it contains the inaffinity parameter called kappa, and orthogonal to K, it contains this object called the HEP connection. You should think of this as a sort of angular momentum of that. Okay? So this is mine, not mine, like, look, this is the connection I'm using, and it's the one that comes from the so-called non-Ripping procedure, which is a procedure from the bulk. All right, with all of this, I can introduce the...
Sorry, you bring that down. Oh, okay, that was step on the
Oh, okay, no, I was just asking, you said that projector is not unique.
No.
So, what are the criteria that you use to choose?
It's called, in the bulk, I'm doing a procedure called the null ranking procedure. So I'm specifying the null hypersurface generator, and the normal generator to the null hypersurface, I'm taking it to be null. And then I'm adapting a sort of Gaussian null coordinate gauge adapted to it, and that's how I use it.
And that kind of projector is unique.
Once you do all of that, that projector is unique.
Okay.
It's unique given that it's things. You could have taken other vectors and other way of parameterizing the model.
This omega A one form, high A in it, you say that points on the transverse direction.
Yes. And transverse on the surface, huh?
Yeah. And so this is like the same thing as the one direction. You said it was the high check.
It's called the HEP connection, and I don't know how to write. There are so many, accents in that name. I'm sorry for Mr.
I'm
HEP.
not pronouncing it correctly, but I think we mean the same person.
Yes, and I think the Weingarten contains also a direction which is longitudinal 12, and the projection is the HEP of the Weingarten. But I can check that later.
So that is related. I wanted,
Yeah. There's a relationship that I worked it out, but it's really very, its spirit is the same. Other questions? Okay, then let me define the null Brown-York stress tensor.
Sorry, maybe I should just ask you, now maybe that's the same relation, but this K that you have, so another way of like building up some structure for these null hypersurfaces is to sort of pick another vector K. Once you have a null vector L that's points on all the generators, you pick some other null vector K that has an inner product of 1 or 2 or something. Is that one of the possible choices I can make here?
That's actually the choice that the null ranking procedure does. So I
that
won't into the detail, but this is exactly what's happening. This K is in one form, but it's the metric dual bulk one form of that vector.
Yeah. But that vector is of course is highly ambiguous. I mean, I can choose it.
And that's why the procedure is ambiguous, is that vector can do anything, and you pick one, you lower the index, and that object is intrinsically projected. Yeah. Absolutely. That's really the geometry I have in mind. Okay, so now Brown-York. So if you remember, the Brown-York of a hypersurface is this object, where n is the normal. And now we have to be careful because this object is an index down, index up. Now you have to be careful on another hypersurface. So the best I can do is to define it this way. For the very important reason that the metric is also not oops, sorry, this is D. The metric is also not being dragged along this connection, so the metric is outside, and so this is the usual wrangler on a time-like hypersurface, and this is the so-called null wrangler. Okay, it's the closest I can write that parallel this. But most importantly, what does this object do? This object, with this connection, satisfies that its conservation law is Einstein equations projecting on that surface. That's why this object and these connections are very important. It allows you to write this equation, where this is matter in the bulk, projecting on n and projecting on them. Okay? So in the following, I will work without matter in the bulk. I will just do Einstein gravity, so we will just set this to 0 right inside. And now this is, again, a rebranding of the membrane paradigm, if you think about it. Because what we did here is that we wrote Einstein equation as a conservation law. And that was exactly what Thibaut d'Amour in '76 and Kip Thorne right after were trying to succeed in set up for a black hole horizon. They rewrote the Einstein equation on the black hole horizon as a conservation law of a hydrodynamic system. The hydrodynamic system is called a Caroyan fluid, and it's complicated, but at least this is formally what's happening. And this should really parallel, again, very much what happens in ADS-T, where if you do the ADS, the Fermat-Graham formulation for the bulk metric, you solve the radial constraint and the time constraint are giving you conservation rules, right? This is exact analog on that. Okay, what are the equations of motion? If I project along LA, this is what I'm gonna call C from now on, and C is equal to write it this way. So this is the projector along LA. The projector orthogonal to LA is going to give me this equation. Here I introduce a particular quantity mu, which is just a combination of these two previous objects. It's going to be useful. For the moment, it's completely ad hoc quantity. But it's going to be useful because it's going to be a phase space variable later on. I'm going to show you this next. Okay, so this is the d'Amour. Sorry, this is the Ricciardo equation. The projection along L, along time, so the time Einstein constraint on the null surface is the Ricciardo equation, and the transverse one is the d'Amour equation. Okay, so these are the Einstein equation projecting on the null surface. Of course, I did the opposite route as the historic one. These were known much before they were rewriting it in this way. Right? So first we know this equation, and then they've been rewritten as a conservation. And here I derive it more like intrinsically as conservation. Okay? And I'm going to focus only on the Ricciardo equation here, which is the time constraint. So this I'm going to show it implies time reparametrization imbalance. That's what I care about. I care about the time, the null time reparametrization imbalance. Okay. Yes?
Explain a bit more why you're calling the second one a transverse Ricciardo equation. The physical, what is the physical
of
the second?
The second one is you should think of, well, actually it's really not think of. Again, a way to get intuition about it in a language that I know you're familiar with is you just push it to non-infinity. And if you push it to non-infinity, this is the body mass loss formula, and this is the angular momentum equation. So this becomes the du and d equal minus 1 over 8 and the d and the d plus 4 over 8, where the role of the body mass is played by the expansion. So it's exactly the analog. It's the null evolution constraint, and this one is the du and a equal, dA and d plus try to remember it by heart, which is just the evolution of NA. So pi a, there is an analog role of an a. It tells you really like I choose my k, I choose my cuts, and how has I evolved the cuts twist and rotate. Okay, now I'm gonna talk a bit about symplectic structure. This is where I'm gonna probably go a bit fast just because the details are just long and tedious, but the whole point, and this is one of the points in which we really take many years. So the symplectic structure of an hypersurface from gravity was worked out initially by Hayward in 1993. 31 years later, we get a bit of clarity on how to think about it. And it's really an collective effort. Ben Chandrasekaran, Anna Flanagan, Anthony Speranza, Prabhu, so many people have, myself, Loran and Rob, so many people have worked on that, Celine Zwiegel, Daniel Gumila, really a lot of people. And the main point is the following. You start with
the 1993 first possibly.
Hayward.
Hayward, ah.
Yes, sorry. Hayward, that's sorry. Pronouncing it in Italian.
Sounds much better that way, actually.
Sorry about that. Yeah, that was the original paper. There's actually also a beautiful paper by Louis Lehner, Rob Myers, Raphael Sorkin, and Eric Poisson. These 4 authors in 2015, I think, had a beautiful paper about it. The main point is you start with the Einstein-Hilbert action and you use your phase space toys. You know that, I'm going to just call it canonical to distinguish it from the theta I have there. You know that if you vary the Einstein-Hilbert Lagrangian, you get equations of motion locally, this is at the level of the Lagrangian plus the symplectic structure. And now the whole question is, how does this guy look as I pull it back to, this is a d-1 form. So it locally can be pulled back to any surface. How does it look when I pull it back to another surface? And it looks like this. So let me first spell out this object. I'm going to write it in a quantity that is fully orthogonal to L and a quantity that is along L. So these objects satisfy this. So what I'm decomposing TAB into the momenta. This is like a momentum extensor into the momenta on the base and on time. And this guy then looks like this.
Okay, is T lower AB two-dimensional?
No, it's not orthogonal to L. It's 3. It's a 3 by 3 matrix. Yeah. This guy is a 2 by 2 matrix. So that's exactly what I did here. I took this 3 by 3 matrix and decomposed it into the space-space 2 by 2 and the space-time 1 by 2. One form, and it's here. And this is a rewriting of 30 years. In the maker.
So the relation between TAB and TAB is not like there.
It's exactly the same procedure here. So you see the index A down, it's not orthogonal to L.
Okay. With the C, yes.
With the C.
With the data AC.
With the Q?
Yeah, it's multiplied by C.
When you multiply by Q, you bring it down. Yes. Oh, I'm sorry. I'm saying something wrong. So let me press. Yeah, I understand your question. Sorry, because it might be confusing with the properties of TAB are the following: TAB KE is equal to tau A, which is different than 0. That's just because this tensor has this property, and then TAB LA is 0. Those are the properties of this tensor. And so what I'm doing is that this object, I'm pulling it together with delta F, and the tau AB, which is the orthogonal to both K and L, 2 by 2, I put it in between.
So if you just have like both lower index of the TAB as two-dimensional.
Let me think about it. So you want to write the, no, I don't think so. You write with QPC. Oh yes, absolutely.
That's I really wanted to make sure.
Yeah. You got it very right. Yes, absolutely. Because you bring it up with Q, which is orthogonal to A. So you get immediate. Thank you.
Sorry, may I just ask in a little bit detail what's the definition of this delta Q? So I'm imagining like this delta is comes from say you have a background matrix and then you perturb it a little bit. So after the perturbation, like the null surface in the original matrix, it's not necessarily null, right?
Excellent point. I'm going to talk about symmetries right now, but to give you already the answer, I'm thinking of deformation of this object that are only intrinsic to M.
Okay.
So my entirety bulk phase space, I don't have it under control. I have under control the phase space of N only.
Okay.
Excellent point. And the symmetries I'm going to focus on are indeed the diffeomorphisms of N only, not of the manifold.
Okay.
And the reason is that I want to focus on that constraint up above, which is time reparameterization on N. That's the only constraint I'm able to reproduce and to represent faithfully on my phase space. So why this is beautiful is because if you're familiar with the SFT and the way you derive canonical SFT, if you go on a time-like slice at R0, particular values of the radius, you should parallel this computation with this. And this is exactly what this quantity is, right? This is the momentum delta the metric, where now the metric is Q. And it takes a long while because there are ingredients underneath, but the structure at the end is particularly simple. Okay. Symmetries, briefly.
But there's that analogy is a little bit it's not perfect, but because in ABS we have some idea of what the reference metric is. We have as a Nolly boundary conditions that give us a reference metric, so it makes sense to absolutely we can define the perturbation of.
Absolutely. The analogy is on the form, but it's not on the interpretation of these and sources. These are not sources. They are not sources on top of the pair. Absolutely. These are just metric variation in the phase space. I agree.
I'll go one of them is an observable one, as a page shows.
Right. Yes. If you were to do the same procedure in ADS, without even thinking of holography, you just take Pfefferman gauge and you project your symplectic structure on a time-like hypersurface at finite radius, it would still look like this. What's missing is the interpretation of physical observable versus pure gauge results and all. But the form is going to be there. Okay, let me briefly talk about symmetries. We have diffeomorphisms. And the generic diffeomorphism can be decomposed as everything else in the direction along L and in the direction orthogonal to L. So the quickest way is to just stick in the projector. And you can show and trust me that the Damour constraint generates this symmetry and that the Ricciardi constraint generates this symmetry. It's pretty obvious because those are the projection of the Einstein tensor in this direction, in that direction. I'm going to show it only for Ricciardi. And so I'm going to, as I said, work on Ricciardi exclusively, so I'm setting y to 0. So my symmetries I'm caring about is only time reparameterization. And how does it act? On L, this is the quantity I'm
Can you
interested in.
just say again, so it also, why did you say y to 0?
Yeah, so I have two constraints. I have the Ricciardi that is about time reparameterization, and I have the Damour which is about space reparameterization. And I'm going to focus only on Ricciardi, which means that the Ricciardi is generating this F times L.
What's the larger picture for why you're making those choices? I mean, what are we after that is informing those choices? Like, why are you choosing to focus on one of these?
Well, this is work in progress. I just picked one, and the one I was interested in about was time. So I wanted to understand the null time instead of how the base works. So I focus on the Ricciardi. anticipating if that object is called C, that constraint, I get the name C to that entire equation. So I can always define a current, which is just the integral on the hypersurface of f times the constraint, the same way we define Hamiltonian current. And what I mean by generates, that's a good occasion to fix it, is that if I have defined my Poisson bracket, these objects truly generate this delta f function. Whereas for the Damour, and we call it PA, PAY, it really generates delta on the fixed. Okay? Where y is this object and where I call this entire equation P. So this is why I kept saying that the Ricciardo constraint generates time parameterization, I mean this equation. And what we are after is understand whether we can set this constraint to 0 at the classical level, or we should rather quantize and define operators as define diff invariant operators as those operators that commute with the quantum constraint. That's what we are after. I'm gonna propose, thanks to the, well, I may even anticipate that. So the kind of, the logic is the following. If I can promote canonically quantize this bracket to quantum operate, to quantum commutators, what does C hat CGS? That's the question. Because classically, I know that this is going to be an action. I'm going to show that.
I think I'd like to understand something. Sorry,
Please.
really basic. So, like the first equation that goes here is a little bit like an Hamiltonian evolution, where you can evolve at different speeds that are specified by f onwards.
Absolutely.
So these are lots. And this is you're just exploiting the alpha locality. I think you choose to evolve
Exactly.
from others. But it's not like a Hamiltonian evolution in, well, that we often see where, you know, given initial data along cut, you can predict what's going to happen. I mean, what happens along a long conference depends on sort of the whole manner that process it, so it's not like a Hamiltonian in that sense. You really have to sort of know everything.
I slightly disagree with that. And in the sense that definitely, if you ask me about what the other constraints are doing, is a subtle question. But if you ask me about where is the information about the bulk profile, it's already inside this object. And the reason is that it contains, and I've been throwing away the two pieces that are important, it contains the bulk profile, but also this, which in the right page is the radiation profile.
The way that it knows about what happens, right, is that TAB, which is part of what defines C, already knows what it's likely to do.
Exactly. Absolutely. It knows about whatever, it knows about how theta dot behaves. Yes, that's what
It's not, but that's data that's given to you everywhere on the hypersurface. It's not data that's given to you on cut. So it's just a way of rewriting initial data on 3 dimensions.
Yes.
Yes.
Yes. And what happens is that, and that's a very important point, is that if you were really to sit down and try to think about the characteristic initial value problem, it's going to be a different question, because there you will start from a cut at the surface, you will specify data there, and you will use this equation to evolve the data. And here we're just rewriting the entirety of the data on the numbers. So, strictly speaking, you can really go a long way with the analogy. If you were to do in the boundary of it, well, let me say on a finite distance, time like at the surface, let me not say the boundary of ADS, this object is really the stress tensor that you use with the Brown-York or Weber-Morgan and Krauss formalism is really using the parameterization of Z1.
Is it maybe the right analogy that I think this is the illusion of the open system?
Exactly. Yes. Well, that's a perfect analogy. And I'll use that occasion because you're very familiar, but maybe people are not. How do we understand the Ricciardo equation? The rectangular equation, we understand it in this way. It's an equation about the expansion of the null rays. So you can think that if the right-hand side is on 0, the null rays do not expand. So you can think of them as just straight train lines, right? One next to the other. The right-hand side contains information about the bulk matter and the radiation. Sigma squared is really the graviton profile. And so you can think of that equation as telling you as the radiation enter in, how the null rays start to squeeze in the evolution. So this is really the physics we're after.
And why were we not happy with the ratio equation and the other? I'm trying to understand why we're writing physics in this way. It looks more. I mean, the ratio equation also captures this physics, right?
What do you see also? I mean, I was describing P ratio equation.
Yeah.
Ah, okay.
Yeah.
Sorry. I don't know.
So, what are we after when we? So this is a rewriting of that information. Right?
Yes.
What informs your choice of how you want to rewrite it?
Right. Maybe I'm jumping a lot ahead, but what's going to happen later on is the following. On this null hypersurface, with this rewriting, I will be able to explicitly see in some simple cases and predict in general that there is a sense in which I can define a quantum operator on M exclusively. This quantum operator will have one feature, which is that it satisfies an operator product expansion, that is delta bonds on N, that is that of a safety stress tensor. So it will behave exactly like a safety stress tensor. How I'm going to see that is by canonically quantizing my brackets and just take the CCOP. Okay? I'm jumping a lot ahead there, but I want to slowly get there. But just to give the answer, what I will be able to see is that there is a central charge.
This C is what we normally would, from the ball point of view, is just the stress tensor twice contracted.
Exactly. The Einstein tensor. Let's see.
Yeah, you want to do Hamilton form, right? The Ricciardi equation is a Hamilton equation.
Yeah,
So the
yeah.
Hamilton form is the quantum mechanics. You just see the symmetric structure and you try to replace quantum mechanics by a computer.
That's exactly the route I'm after, but it's important to relate because that's not the way that we typically in the community approach these equations, right? We think of them from the point of view of I define my cut down here and I evolve my data in this null sheet, so it's important to make the link with the various approaches. But indeed, this is very similar to a space-like canonical quantization procedure, except that it's not the hypersurface system.
That's the reason why you want to go from here to there.
But
Yeah, let's keep going. I think,
yes, sure.
Yeah.
But because I'm already anyway planting the seed for the next, so I'll just let the plant grow, and we're gonna find the PE. So it's perfect. So yeah, so we were stopping here for a moment. So what I want to do is focus on time reparameterization. So I'm gonna just focus on F. How does that act? Well, it acts by a Lie derivative, right? So it's just a diffeomorphism, and so in particular is the Lie derivative between FL and L, which is simply minus LFL. And I use the notation L acting on something means the vector field is acting, right? So this would be minus LA partial A of F times the vector field. Okay? And so I will stop here if I haven't had another symmetry in my exposure. And this is the second one. Ultra locality, I'm going to expose this later on, and the other one was conformality. Conformality means there's no intrinsic notion of length. What does it mean in practice? It means that, and unfortunately I erased it, in the definition of the null hypersurface, the geometry was this and this. So at the classical level, at least, I can simply multiply this by an over-vanishing function and call the new object L prime. Both equations are satisfied. if lambda is positive. Okay? Which means that intrinsically, this is just a way in the phase space to see that there's no intrinsic notion. It's exactly the same thing. And intrinsically means that I have another symmetry, which is lambda on the phase space. And I can see actually my equations being covariant with respect to the symmetry. And now what I'm going to do is something very smart. That's why I didn't do it. My collaborators did it at a certain point. Then I had to collect the pieces and try to understand what they did. But it was a very smart point, was to understand that this lambda could have been, you can make it equal to LFM. You can choose that lambda to be LFM. In that case, what you have achieved is that the combined action delta F plus delta lambda on L is zero. And now, when I mean collecting the pieces, is understanding what they did there. And that's the beautiful part. What we did here is essentially establishing a vector structure, promoting this L vector field to be a vector structure. And the parallelism that you should draw, and this is not a parallelism, we will go all the way, is with CFTs. If you take the conformal field theory, you have a background matrix mu, and you have two symmetries. The conformal transformation are a combination of diffeomorphisms, which do not preserve the symmetry, and Weil transformations, which also do not preserve the symmetries. And in conformal field theories, what you do is that you choose omega to be minus lambda alpha C alpha, and you combine these two transformations to get delta G equal to 0. That's how you define your background structure, that's how you write down your beautiful word identities, right? We did exactly the same thing here. So we established L to be a background structure, and this will be extremely important later on. Anticipating when I will, hopefully, when I will quantize or describe the quantum aspect of the theory, I will go back, and it will be very important as a check. I will have a conformal anomaly. Where does the conformal anomaly come from? In the CFT we know it comes from Weil. Diffeomorphisms are not anomalous. Here it will come from lambda, which is indeed the same as Weil on this nanometer.
Is this choice in some way related to parameterization?
No, at this stage kappa can be different than zero. And since that L is 0, it's pure gauge, so I'm gonna just pick a value and adapt my coordinates. Okay? So then I will write equations that looks less covariant, but they're covariant. Okay.
So does this choice fix kappa or does it?
No, kappa transform. And even the combined action. I can show you if I remember it, otherwise I can look it up in the paper. Delta N plus delta lambda kappa is equal to is the infinitesimal one is equal to F into kappa with this choice of lambda, the one I made, plus dv squared. That's how it transforms. And yes, no, I think it's this because it's a one form. It has the one form piece, and then there's an extra shift. This is very important later. That's how kappa transforms.
When you say transform, what is the first? This is the shifting up.
Is the composition of delta F and delta lambda, where I pick up lambda to be this exact, what is it? This exact value. The reason is that this internal scaling and this time reparameterization, they act on L very similarly, but on kappa no. They have a different action. And so even when you make one equal to minus the other, kappa still transforms on them.
And the resulting kappa doesn't create any particular fixing equation.
No. Okay, so I'm just gonna very quickly derive the brackets. So I set delta to 0. Much weaker than that said. And so now I take the symplectic 2 form and I just write it down. And his object is gonna be equal to the following. I'm gonna do one very important thing. I'm gonna extract the area element. So this is the metric on the cut, and I'm going to write it as omega times q bar, where this q bar has unit determinant on the cut. So this object is there, namely the area of the cut C is going to be the integral over epsilon 0 C, by which I mean just to measure the coordinate measure times this omega. This is just the area density of the base, and then the symplectic 2 form looks like this. And that's why before I was insisting in this combination, calling it mu, because I just couple it together as the variable conjugate to omega on the phase space. So this is my symplectic 2 form. It has spin 2 data. This is traceless, symmetric, and orthogonal to L and K, so there are 2 independent degrees of freedom here. And this is unit determinant, symmetric, and orthogonal to L. There are 2 degrees of freedom here, so these are the spin 2 modes. And then the spin 0 modes is the area and this mu guy. This mu guy you should think, morally speaking, to be the inaffinity, and it's kind of clear that the inaffinity is the conjugate variable to the area. It's not physics, right? And okay, now the step is to...
sorry,
yes?
This area you define over there, is that just a definition or it matches actually the area on the cut?
Well, it is the area of the cut. Probably it is. Sorry, but...
I just remember that in the Europhase space case, like the area is actually some integral of some Noether charge, but to make it to be exactly area, you need to make the surface to be extreme. But here you don't have any extremality, but it's...
So I can write down the charges if you want, briefly. That's actually, I think it's a beautiful thing. So let me write down the Noether charges. You derive it from here by contracting with the vector fields, and you do your usual canonical phase space analysis, and you give the endpoint. What are the charges? Maybe off shell, it's even better. Off shell, they are equal to F times C, where C is the rechargeable constraint, plus the integral over the cut of omega dBf minus F dBf. These are my charges. Okay? What do you read from this? This is not a second theorem, right? What you read is that when you go on shell of the rechargeable constraint, it becomes a corner quantity. So this is the first thing that I wanted to show. That's a good check. And then you read that this is the charge of a cut. So let me specify, since you asked, let me specify F to be a constant independent of V. This should give you the Hamiltonian of the system, right? The Hamiltonian charge of the system. And QF0 is equal, you see the other guy that you pick up, there is a minus sign that is just there for the ride, F0 times T. Because the relationship between theta and omega is theta is dV omega over omega, and so you can write this as theta times omega, and omega is just the covariant measure. So it's theta. The expansion is the Hamiltonian charge. Okay. Interestingly, if I take a boost charge, so I take a boost around d equals 0, suppose I put my cut at equals 0, I take a boost whose fixed point is d equals 0, I plug it into here, and QFB, you see now I turn on this guy, is going to be equal to the integral of FB times omega. If FB is a constant, 2 constant of the base as well. These are all of the cut. These are all of the of course, sorry about it. If this is a 2 constant, this is FB times omega. So the modular Hamiltonian, modular V partial V Hamiltonian is the area, the Hamiltonian is the expansion.
I'm sorry, coming back to this exclamation mark. This exclamation mark, you made some kind of gauge choice, right? You made some choice. shape of my cuts, or I can choose the infinity. Not sure what else I can choose in terms of how I feel the evolution line. And I'm trying to understand what this is in mathematics.
Yeah, morally speaking, that's what you can choose exactly. So the shape of the cut or the infinity. Exactly.
What does that have to do with the explanation?
So exactly. So that's why on game choice, I'm not sure I would use that wording, because here what you're doing is that you have a symmetry, and you are reducing the symmetry to have a precise shape. So you're not imposing anything on L itself at this stage. What you're imposing is that among your symmetries, you are restricting your attention to some symmetries.
That's usually called digitals, right? It's the same as the equal cross y, and you just choose only some space which keeps y cross y. It's essentially y cross y.
Yeah, exactly. No, I mean,
it's a damage, but it's
okay.
usually gauge choice by using a metric. Usually here you use error, and then to fix it, right?
yeah, I agree. It could be called the gauge choice. I'm not sure that that's. I was thinking more of gauge here as fixing some of my geometric data to be something. That's what I would call a gauge choice, and that was just a fixed symmetry fixing. But I agree, in other contexts like in CFT, that's called a gauge choice. So you're right. But I don't know whether you were thinking of fixing some geometry. This does not fix the geometry. This just restrict the symmetry.
Geometry is fixed to start with, right? It's
Right.
a null, Hypersurface, and everything we're just discussing is how to slice it up. And I'm trying to understand what the physics is in that.
Right.
It's different from the G mu, I mean, like I was saying, like, it's different from the kind of delta G mu that appears in asymptotic regions like APS, which are picked out by asymptotic boundary conditions. It's completely clear what's going on. I'm confused by the fact that here we just seem to be rearranging slices on the fixed geometry, but neither of those slices are in the preferred array values or cuts.
No, there's no preferred cuts. Yes, I agree. All right, so
maybe for sure 5 more minutes.
okay, okay, for sure. And then after
We're
that,
generous with blackboard talks, and you're like, no.
okay, great. Okay, so I'm just gonna maybe discuss ultra locality, and then I close 2 minutes on the quantum. So this can be inverted. It's a horrible disaster. You might think it's very simple because your data are this, and the inversion of that is extremely simple. Let me do it. It's a symplectic pair. So I'm gonna call mu1 mu of x1, which is mu of v1. I'm gonna introduce coordinates on the cut as well, where I think of the cut as z bar and v about my null time. And then that guy just read mu1 omega 2 is equal to, I guess, 8 by g. Yes, that's correct. Delta 1. Right? It's just a symplectic pair. Heisenberg, by this I mean delta of v1 minus v2, delta of z1 minus z2, blah, blah. And then you may think, okay, then this is the spin 2. Then what creates a mess is this object there. Because that was one of the phase space variables for this spin 0 pair that now populates the spin 2. This creates a non-trivial action, and so the way to do it is that you're going to see that some spin 0 brackets will not Poisson commute, some spin 0 quantity will not Poisson commute with spin 2 quantities. That's all you're seeing. It's not that loop, if you want, right? And so I'm not going to write down the explicit expression, I repeat long. The paper, but I just want to give you the main message. The main message is the following. Mu1 and sigma 2 does not commute as a function of sigma, and it contains delta of z1 minus z1 z2, delta of z1 bar minus z2 bar, times a complicated function of v1 v2 that I'm refusing to write in the chart. Okay? And morally speaking, all the others that are sigma q and mu mu, actually mu mu is not a quantitative variable, have this form for a different f. So I'm just giving you the gist. What is the main take-home message? The main take-home message is, as soon as I turn sigma to 0, which was my radiation that was entering the surface, of course everything dropped and I have just a spin 0 pair. That's the main one more message. Of course, if you drop this, you just have this and it's extremely simple. And it's just area and time. Area and time. Area of the cut and time for a ball. Those are the symplectic variables. As soon as you turn on radiation, things get more involved, more entangled, as it should be. But one structure that you have is that, not the this. And this is the pencil. This is the ultra locality. This is the fact that no matter what you do, no matter how non-perturbative the graviton you put on, you're still gonna split your physics into independent analysis. Okay? And therefore, now, that together with conformality, together with a lot of things that I hinted toward, now the seed that I planted grew up, and I can talk about the quantum in 2 minutes. So what is the proposal? The proposal is the following. C itself, this Ricciardo string, does 2 things. First, it satisfies an algebra. At the classical level, it satisfies an algebra. It generates time translation. And it's ultra-local. If you think of this time translation as a DFS1 analogy for a second, you just are talking about a Virasoro system at the quantum level. And the prediction, therefore, is that this guy, promoted to an operator, and this arrow is going to contain a numeric factor, which is important, satisfying at coincidental point this relation. This is a very small c, and that is a very big c. There are differences. And as customary for an ODE, I'm just putting here just the divergent pieces.
And what is small c?
This small c here is the potential central charge of the system.
No, I understand, but what is it in terms of?
I'm going to compute it explicitly in 1
Okay.
second. Yes. A priori, for the moment I did a prediction, so I don't know. It depends by the field content of material. But later on I'm going to check. This is for the moment, it's just a prediction. I'm not saying that I've computed it in full generality. I don't actually know how to compute it in full generality. I can only predict it in full generality, but I can compute it explicitly in simple cases. For instance, the simplest case, well, okay, let me just briefly, before I go into the case, make one comment. So this is just the OPE of the stress tensor in the CFT. It's just the vanilla guy, and from here to there, you know immediately that if that's the OPE and this is the classical bracket, the quantum bracket is just this. This you know immediately. This is just the infinitesimal portion that populate from here to there using this. Okay? So what I'm introducing is an effective one-dimensional conformal field theory whose fields, and this is going to be related to your question about what C is, whose fields are really, and I raised the symplectic to form, but are really just the spin 0 and spin 2 data. All the geometry itself. So this geometric data organizes themselves as an effective one-dimensional CFT on the narrative. Okay? Now,
So why did you say it's one-dimensional? What you mean 1 plus 1?
so this is a chiral sector of a 2D CFT. So it's a one-dimensional. The piece I have access to is one-dimensional.
Sure.
There is the other part that probably is in the other
Yeah, I'm
dimension.
just wondering because of the scaling of the identity piece. That
Yes.
was like 1/, it has the scaling of a 2D CFD.
Yes, exactly. That's why it's the chiral sector. And if you count, let me do it. Can I have 2 minutes to finish the counting? So, okay, so now, this is a prediction. Can you do it explicitly? And the answer is, in full generality, is a disaster. You would have to do conservage, you would have to do a lot of funny geometric deformation quantization thing that it's hard, in general even, and here even harder. But I can do it in 2 cases, which are already not. One is very simple, the one I'm going to do now, which is I throw away completely radiation. So you just pin 0 data, time and area, and I quantize that system, which is pretty empty if you think about it. The other one, check the paper for details, is the perturbative addition of the gravity. So what I'm going to do in the second case, which is much more interesting, is that I'm going to take my Ricciardovi constraint, which should be written somewhere in this coordinate, in this metric, is just like this. Okay, it's the same equation I wrote before with theta, I just massaged it. Is that I'm going to introduce this graviton perturbatively engineered. And then also I can compute that thing even on a time-dependent background. That's a hard question in general in gravity. Time-dependent backgrounds, perturbation. So there also I have the computation of what little c is and the proof of this OP. When the graviton sigma is non-perturbative, I don't know how to quantize these brackets, and this is complicated. I can only make it as a prediction. Okay, let me do it.
C depends on the whole history of the radiation.
Yes.
Right. If it's a time dependent.
Yes.
C depends on the whole history.
Yes. And there's also another question that I haven't even touched about, which is the fact that time here is between 2 caustics, so I have to choose a time that stands from -infinity to +infinity between the caustics. It's possible, but it's a choice of time. We can chat about it later, that's longer. Yeah, I see you're sorry about it. Just 1 minute.
Let's say something else.
It's because of the joke I made about Stefano t-shirt. That's where I waste all the time. It's like, 40 meals went away. Okay, so now if I set the shear to 0, this bracket drop, of course, all of this drop, also mu, and mu was a function of sigma. I have a symplectic pair, and this is now a simple game. You can just forward this to the commutator. You can work out. Its OP. It's gonna just be equal to there's 1/2 pi I to be careful about. So it's 4 GH bar over d12 minus R epsilon. I'm going per cut, so now this is only time. Forgetting about the ZZ bar direction for a moment. And then you have this OP, and you have, I'm throwing away sigma, this stress tensor. And now this, you just go back into your preferred review on the beta gamma CFTs. It's a beta gamma CFT. It's a curved beta gamma CFT pieces. It's OP with this stress tensor. So even without computations, you know everything. You even know the little formula, even the conformal weights of mu and omega from C, but you can just compute it explicitly. The weight of omega is 1, the weight of mu is 1, the weight of omega is 0 in particular, so it's a C equal to beta gamma CFT. And that 2 is the number of fields per array. So that's why you have all the omega and mu, you have 2 fields and it comes to. If you introduce the graviton perturbatively, you crunch the machine, you cry a little bit, but okay. Suppose you crunch the machine, it's as easy as doing that, you get 4, because the perturbative graviton has 2 degrees of freedom. So you really get 4 again when you reintroduce C.
And these are both just free field theories in that sense?
Sorry?
These are free theories?
So that's an important question, right? To make sure about what this is doing, right? So this is the entire gravity thing, but when you turn off the shear, this is a free theory of these 2 quantities. And when you turn on the graviton, if you do it perturbatively, it's again a free plus free T. If you do it non-perturbatively, it's not, and that's why I don't know how to compute the quantity. And okay, so maybe I just finish with one sentence, a bit of slogan, because given the time I cannot explain it that much, so I have to make it as a slogan. But this, I'm very excited about this feature, because it goes back to a very old problem in gravity, in quantum gravity, which is the problem of time. It's the problem that when you want to quantize a gravitational system, you're always facing the big dilemma of covariance. Which time do I pick to do the quantization? Is that unique? Do I have a family of times? Can I change the time? So here what we are seeing is something very subtle. It's a mechanism to have classical covariance and a preferred quantum time. Because as you know very well, in a CFT, if I have a central charge, now different times, in that case different reparameterizations, are physically inequivalent. So I can act with the Ricciardo constraint of my state to create an inequivalent state. This is thanks to the fact that I have this. So, slogan, sorry about it, classical time covariance, gravity, and gravity quantum time, physical inequivalence, so a physical quantum time. Okay, I didn't explain this very much, I don't have time, but I could explain it later if you want in detail. I'm happy to take it as question. I really have to conclude, I suppose, right? So, thank you very much.
Since you mentioned consecutive state formation, quantization, I'm just curious, do higher order terms in H bar concern you?
In doing which one? In doing the full one? Like you mean?
When you go from Poisson bracket commutator.
Here it does not, because Heisenberg pairs, so I can just do it here. This is stable against H bar corrections. If you go and check Consensus formula, what it tells you is that at the next order, it has derivatives of the right hand side.
Yes.
Which is 1.
Yeah.
So it just goes to 0. That's why when you quantize an Heisenberg pair, that's non-perturbative. When I do it for the graviton, it's the same if it is perturbative, because again there are free theories. So I just in the non-perturbative case, I'm very much concerned about those H-bar corrections, and
that's just the problem of. So because of that, this whole thing only is supposed to make sense in effective field theory.
Well, this is non-effective, but okay, it's a very simple. If you include the perturbative, if you include the graviton, this, yes, is too only ineffective.
It doesn't even make sense beyond that. Like it seems like you're saying these calculations are hard, but is it hard or is it just impossible in this spectrum?
Well, it depends how mathematically inclined you are. If you ask me, it's really hard, it's really impossible in the sense that I'm violating some mathematical structure. I don't know how to react to the question, maybe. If you ask me as a physicist, do I expect this to happen, but C will not be just some logic of counting, then
so
yes.
Is it a better problem than trying to phenomenally quantize gravity in 3+1 formalism versus space and time?
So, great.
Sorry, whatever I interrupted your question.
No,
That follows up in a beautiful way. So, it is a better problem with respect to time. If you try to do that, time is a game showstopper. And here, time is not. In that regard, it's a better problem. In the regard of will the thing converge, is it really finite? No, I don't think it's a better problem. I think it's essentially of the same nature. Yeah.
Can you explain again in what sense the central charge, having a central charge makes a preferred time, and it's very particular on which?
So, yeah. So, which time does it take? It's a very long story. Because even classical is not simple to study caustic avoiding times in general to see what expansion does. So you can pick up a time. In particular, affine time would have typically the expansion going to plus or minus infinity with caustics, and so Here I'm not doing a fine, I'm doing any times, but you have a family of times that you can study that are caustic avoiding, a family that are not. So even classical, it's a whole
Why do
mind.
they have to be caustic avoiding? What's wrong with the caustic? I mean, I'm trying to understand why you're, shouldn't the formulas somehow make sense of the caustics intrinsically? Since they are part of the physics?
You should, but if you can do it, it would be great. No, for the moment I don't know how to do it. You should. I have a couple of comments to make about the caustics. So that's what happens, right? This is a one-dimensional safety per point. I didn't even talk about the entirety of the cut, so there is point, and when they merge, you have to talk of how they interact. It's very hard. The comment I have about that is, by the setup, I have been using something sneaky around, which is that I have been using in the quantization a time that goes from -infinity to +infinity, between constants.
But if you do that, you could have done that between any finite pieces as well. I mean,
Oh, sure. Between any finite pieces, but in particular between the constants. And if you do that, you can check that if you take just flat space, you take an array, and you want to set up this problem, you can set that such a time is not, it is caustic avoiding. It has an expansion, there's a family of times that go from -infinity to +infinity between caustics, whose expansion goes to 0 at the constants. So there is a relationship. I'm not saying that it's one-to-one, but there is a relationship. Now, how do you glue caustics? I mean, the phase space between and after caustics, that's a beautiful question that I don't know how to do it. I have one comment to make, is that in writing the Reshado in this way, I wrote an equation that goes to 0 at the constant.
how is this different from, like, if I, maybe it's, I don't know, I'm going to try it anyway. If I just consider electromagnetism, classical electromagnetism, and I consider initial data given on some time slice for, the gauge field in whatever.
Okay.
And I could discuss, I could somehow foliate that three-dimensional surface into two-dimensional slices and think of that as some kind of evolution. I could ask about, for example, how the choice of gauge evolves. Maybe I have Lorentz gauge here and it evolves into some other, And I mean, I could change that. I have a lot of gauge freedom. I could try to write down equations for all the different ways I could change that. But it wouldn't occur to me to quantize that kind of evolution. I don't understand how that's different.
So here, okay, I don't know whether this is gonna help. The analogy I draw again, okay, maybe with the subtlety of defining observable, etc. But the analogy I draw is with ADS, where your stress tensor is doing this, right, at the bottom. It's imposing the Hamiltonian evolution of the bottom. The stress tensor that you derive from the bottom.
In ADS, because of the asymptotic conditions, there are things that we can expect from a metric in the pulp that are not pure gauge.
Yeah.
So it's very important for my argument that here that's not the case.
Okay.
It seems to me like a study of an evolution of gauge choices along some slicing, which in this case the slicing itself is part of the gauge choice. But that's not really a physical evolution that we can only consider quantized.
Isn't it the electromagnetic would be like a drop composition where you promote the gauge constraints to represent every point? I think that's the idea.
But that's what we need to do when we want to actually quantize the theory, meaning we're interested in the three-dimensional initial data and we want to evolve them forward. Right? And then we need to face that kind of problem. But here it's more like we have a kind of a classical situation to start with. We study a classical set of initial data, and then we ask about all the different ways that we can change the gauge for electromagnetism on that initial data, and we rewrite that as like an evolutionary equation of cross slicing of the three-dimensional and two-dimensional spaces. And that's, if it's like that, that's not something we would think about as wanting to quantize. Because that has nothing to do with the actual Hilbert space.
But the physics of this system is just rechargeable, right? So why would you say it's, I mean, I would like to quantize that physics. Is that a question that makes sense with respect to your, it's gauge invariance and problem, addressing this problem?
Well, I think maybe the issue is to what extent you can think of the null hypersurface as being like an initial data surface or more like an evolution, right? And I think it's more like an initial value surface, right? Because you need like an enormous amount of data. I mean, it is like, you know, if I give you half of a space-time and I don't tell you how to continue, you don't know anything on continue. So there might be constraint equations like gravity. So you can't just continue the metric arbitrarily with content, but still you don't know anything about the other half.
Right.
It's very different from like that evolution in the usual sense, really.
Absolutely. And I think that's the problem, right? Because this approach is more of an evolution on the upper surface instead of an initial vector. Right. So that's where I think we are.
So should I think of these in terms of, say that I want just to do canonical quantization of gravity? Is this analogous to quantize the momentum constraint before it goes again? Is that the idea? So you have the momentum constraint on the slice, and then you have the Hamiltonian constraint to evolve that slice, and you want to promote the momentum constraint to a quantum operator, and then you pose it.
This is more related to the view of this null hypersurface as an initial value hypersurface, rather than, I mean, it's a bit ambivalent in the description, right? Because you want to think about these two evolutions of quantizing the constraint in this direction or the Hamiltonian in this, and then I'm telling you I'm doing this, right? And you can think of it as, oh, that's the initial value surface, or you can think of it, that's where my data evolves. And these approaches definitely imprint the spirit of this is where my data evolves. Because essentially I'm thinking of this age as becoming my C that I want to promote in operator. And in Raphael description, it was thinking more of it as the initial value data, and therefore it doesn't make sense to refer to two cuts and the evolution of two cuts. Your question was more related toward, I think, Raphael understanding that surface rather than mine. But it's ambivalent. I'm not sure that it's, I don't know, maybe you have a better understanding of which one I should think of, but...
If it's not a closed system, if it's not isolated system, it's the same thing. You can have the equation with some, whatever you can count. Right? And that's the same as you can choose the initial data. Right?
Yeah.
The fact that you do initial data, knowing this is not enough, right? You can choose.
Right.
And the same thing as like time evolution, but it's all consistent.
Oh yeah, absolutely.
It's the same thing.
That's a fair point, indeed.
But what's the analog in electromagnetism? What's the analog, just going back to this example of electromagnetism, what is the analog in that case?
So you have some electron dimension as the same. It's all consistent.
Is it useful to then
I don't know.
quantization?
But I don't know, but that's what this is doing, right? Because it never knows.
No, it doesn't know what's coming in. That's an input, right?
Yes. No, clearly, but by the way, I should emphasize, this is not quantum gravity, right? I'm not quantizing gravity, but that's one constraint in one direction. It's extremely little, right? But
I guess what we're all trying to understand is if you did this for electromagnetism, what would you, which we know how to quantize, if we did this procedure, I think we could do the same procedure of looking at hypersurface and trying to understand exactly, and trying to understand the quantization condition. What would that teach us about quantum Maxwell theory that we understand very well? Would it teach us something?
I'll let you know in the coming days. haven't thought about it for electromagnetism. Definitely.
I think that's a better version of the question I was trying to
Okay.
get, and I think it's really worth understanding.
Yeah, I agree.
This is hard part, and
Yeah, you want to see if it's useful for
yeah,
something.
exactly. I think that's a good one.
But it's important, that would also be impossible for an interactive computer to understand it in this language, right? Because the algebra is believed to be empty on no hypersurface. Maybe the algebra is not empty.
You have to explain to me a bit later or
Yeah, the algebra trivializes.
Yeah. Let's see if there's any other questions.
So maybe to pile up very quickly on that, the direction I was going, but definitely doing for myself would be extremely interesting. I'll think about it. But the direction I was going to go now was to introduce the other constraint, which is the Moore one, the one on the base. Because I think that even that already could make all this story a bit crumbling, because it will allow you to connect via symmetries different null hypersurfaces, right? Then null rays on the same null hypersurface. So that was already something I was going to think about. One thing that I like, and something I wanted to mention and I did that time, is that you can go on infinity, at infinity, you go like this, with this null hypersurface on asymptotically flat. And what this CCOP tells you is essentially that there is a Bondi mass fluctuation, that the quantum level diverges, which is something that in 2017 Raphael and Aaron you discussed from a completely different perspective. And so and I found a very similar result, like I didn't check of course, so the next but the spirit from this quantization, and so I would be very curious to see if it's not coincidental. So that's one piece of physics that I like, because it connects to something very concrete that has been already worked out, and so it gives, if it works, I mean, if it works also the reason why it diverges and the shape of its divergence, it will really give some support of doing this, right? Which is maybe much concrete and simple, but that already would be something very interesting. That's the first thought I had to connect it to something more concrete.
So the C1, C2 of E that you mentioned, from the ambient perspective, can I think of it as a stress tensor of E? Like on the null surface? Is it the same thing?
From the ambient perspective?
Yeah, the stress tensor. You have the stress tensor along the null surface.
Yeah.
Is it really, that's the origin of this OP? The C1, C2 is a stress tensor of E?
So
stress tensor.
So eventually the long detour is the following. You start with Einstein equations, you project it twice on this outer surface. You wanted to write it like this because you're a classical person, so you want to write it as the Berkeley, but which would be equal to matter. You want to write this equal to 0 as being this equation, but then eventually you backtrack, you call this guy C, and you promote it into an operator that is an operation of E. Eventually what you're saying is that on the null hypersurface, this is what you're doing. So it's really the Einstein tensor projected that you're treating.
So it is really the stress tensor of E versus the matter.
If you have external matter, your C prime with matter is C without matter plus matter. It's just that. With the plus, because the way I've defined it here is to the left. So yes, it is related to that. You can think of it as the stress tensor for the spin zero data, that are gravitational data. So we don't typically think of giving it a stress tensor interpretation. But that's exactly what the Einstein equations are doing.
So if I have zero stress tensor, you get a non-zero central size?
Zero matter stress tensor, yeah. All we computed were just gravitational central charges.
Okay.
Yeah, that's why there's something interesting with time. I wouldn't have even mentioned the problem of time if this was entirely due to the matter center. This is gravity itself that is providing this central charge.
Alright, let's
Thank you. Again.
Very nice questions. I'm Luca, by the way. So the eventually policy will come. Tomorrow, light values. Yeah, and light that's the physics. We don't have to decide physics, we have physics. You don't have to like so those are three analogies to figure out.
So the analogy approach with vertex operator research.
That's all.
But there's
Take a little note.
We really don't know about that.
why it's globally there, but it's not globally. Right? And then of course, those are more.
Yeah, no,
it's the same thing. If you just globally, you want to see global physics, you have to. And then of course, it's vibrating.
This is scaling, which is why.
Yeah. Zero scale measuring the global physics more seat.
This way, equivalent to static quantized vector constraint.
That's very interesting. Thank you. I like that comment a lot. Because I've been thinking about costing a bit, but it's very complicated.
Yeah, it's complicated because like almost all the words in the computation, most of them.
Yeah, we don't use exactly
Figure out this accelerator, what's the residual
just to understand
global value by that's the oh, absolutely. I mean, that's why I can imagine the same thing happening.
Understanding biosymmetry in the global
residual. They are supposed to do something I think, yes, you want to do the orthogonal direction as well. Otherwise, it's just equal theory.
Just slicing it up.
The first step is just simply just solve it and then what's the
We
violation.
still discuss all the different ways we can slice it up, and we could ask about some.
Anyway, it was great.
Thank you very much. Thanks a lot.
External data, maybe what's going through it. External topics. It just seems to be zero.
Thank you.
Can I just ask you one more question about like
Is it really
or something maybe you have said in the beginning, like so you choose to quantize more hypersurfaces because it's simple or because
so
there are things has been done before. I never think that this
every
if you try to do quantization of space like hypersurfaces and you do a Hamiltonian analysis, the Hamiltonian is done is multiplied by Lagrange multiplier. Yes, so it's just Z. This equation is just Z. There's no time evolution of observer. What that is telling you is enough. Is what you should bit about the problem of time. It's just because time is a full change direction. And there's nothing possible. That's what that is classical.
or this is different between that Hamiltonian constraint and ratio.
It is this, but on 9. And when you put it on 9, then it is